Hello everyone, my name is Roy Jafari and I would like to welcome you to another video. In this video, we're going to talk about a different regression model that is going to be very specific for specific data. We're going to discuss logistic regression. And logistic regression is only applicable when our dependent attribute is binary. We've seen that when we use regression, all of the times we actually have numerical dependent attributes. But logistic regression is a very popular method that actually can handle dependent attributes that are binary. And it's going to actually do just better than that. It's not going to be a classification model. It's going to be a classification model. It's not just going to be, a classification model that tells you 0 or 1. It's actually going to give you a reliable probability value for your future cases. Okay, let's forget this slide. Alright, we'll start with a few recap, and after that we'll see sort of like a gateway to model that we're going to use to sort of get our way into the logistic regression. The model is called linear probability model, which uses regression to go about the task of classification. We'll see how it would look like and its shortcomings. And after that, we'll discuss logistic regression and how it's better than linear probability model. And of course, we're going to use an example throughout the video, and then we're going to offer some summary. Okay. So we did discuss what is regression. Regression is when we want to estimate the relationship between dependent attribute and independent attribute. So if we have sort of independent attribute, you want to find the relationship between the independent attribute to dependent attribute. We use regression. Most of the time, we use regression for prediction because our dependent attribute is numerical, right? If you remember, that was the difference between classification and prediction. But how about if we wanted to apply, regression methodology, the way we have an equation, find the betas, so on and so forth, into a classification problem. If we have a binary dependent attribute, can we use regression types method? I mean, regression only works with numbers, right? You have number everywhere, so you have to sort of like find coefficients that you multiply with these numbers to sort of output something that is similar to your dependent, right? So that's what we are going to do here. So the first thing we will look at is the example. So this is the example we have. We had seen this in our classification video. So we have two predictors. We call them x's, and we have a dependent attribute or target. We call it y, and we want to use regression here to find this relationship. I mean, like I said. Normally, this wouldn't be possible with regression because this is a binary attribute, and so we want to sort of like go on an adventure, see if regression can help us here. So this is the algorithm. This is what we're basically trying to do. We're trying to connect the independent attribute to the dependent attribute. So what I'm going to sort of like suggest as the linear probability model. How about if, instead of sort of like looking at, these default value, which is like, the customer defaulted on the loan or not, start thinking about, looking at them as probability value. I mean, we do know that these are, done deal cases. I mean, these cases have happened. So let us look at no as the case of 0, or like probability of 0, this person will default, and 1 as probability of yes, this person will default. So we will switch the default or the target from a binary, from a categorical attribute to a binary numerical attribute, right? So we call these all 0. We call all of these 1s. Now, because these are number, we can use regression, right? So this is our estimated probability value. So this is y, or our p hat, and we are going to use these numbers with these numbers for regression, right? I mean, this is a number, and those are a number. We made some assumptions there, but you know, as far as what computer concerns, it's just going to run. I mean, it sees numbers, and the algorithm is going to work on numbers. So it's going to work, we're going to see what we're going to get, right? Let's go ahead and do this in R. So let me open my R here. All right, so this is R, right? So this is the data. Of course, you're going to have access to this data. I will provide the link for you. So this is, you know, the data. So once we run this, I can check, for example, that is my data. This is the same data, but I have added a default binary, the way we saw in the slides, and then we can go ahead and have a, you know, probability linear model. We use just a linear model the way we used in the previous video. You know, default binary, income, score, and our data is DF. So once we run this, it creates our model. So let me put PLM here and run. And these are our intercepts. And let's look at the summary. So once we run the summary, we do see that, you know, the score is significant, and also the intercept is significant. The income is not very significant. But anyway, you know, let's go ahead and look at the prediction. So whenever we want to sort of like see the prediction of those values, we can actually use the function predict. So if I run this, and you know, I've created the values here, and look at the prediction, right? So if I run this, now I can see, you know, what the model is telling me about each of these numbers, right? So I, for example, you know, see that I have a negative 0.04, and that's supposed to be a probability value. Do we have a negative probability? Or I do see a number such as 1.23. Again, you know, it's supposed to be a probability value. Do we have a probability larger than 1? So, you know, now slowly but surely we are starting to see the disadvantages of just, you know, using the model as it was not advised to use, right? So we sort of like, you know, look at those probability model and like gave it to the regression model, and regression model is just going to look at it as numbers. And because of that, it might have numbers larger than 1 or smaller than 0. I mean, for it doesn't matter. So, you know, 1 could be, you know, sort of say, yeah, I mean, you know, the fact that the number is large, it means the probability is probably large. And probably this data object is going to be the case of defaulting yes, right? So let's go ahead and look at the data. Here, let's see, let me go back to the data. Okay, let's look at here. So one thing that has changed here, let me show you. So these are in the starting indexes from 1, pay attention, to 20. In the slide is from 0 to 19. So let me go ahead and update these very quick. All right, so there's less confusion. All right, so you know, for example, for the case of 16, it's 1.23. I mean, of course, we are sort of, you know, sure that we're going to see a, you know, yes default, right? So case 16, you know, rest assured that it's a yes default. Or let's look at that negative 1. I mean, it's a very small number, so it's probably like the one that, you know, leads to a no default. And let's look at what was the number, was 9. So case 9, of course, it's a no. And, you know, the everything looks like that. It would be no, right? So what we are seeing here is this model is working, but, you know, it's kind of not the best we can do as probability value. How about we use some functional, transformation of this data to make sure that we could actually use these values as probability values. I mean, if we have that capability to use these as probability values, right? Now, in the future that we want to, think about the data that, the future data that we want to actually make decision, we would run that by the model, and it would give us a probability, right? So let's say 70%, 30%, right? And that would be very meaningful, because now we don't have to sort of like have a clear cutoff. We would say, okay, the probability is 70%, and the risk of actually giving the loan is this much. So now you can actually do calculation to find the maximum expected value of profit, right? Because this is probability, and that's a very meaningful achievement. So because the probability value are meaningful, we want to move from something that can actually give us. So the logistic regression is basically that. I mean, we use a functional transformation within the model to make sure that the outcomes are going to be probability value. That's all there is to it. So if this was the sort of like, the general linear probability model, so this was the linear probability model, we move to this other, a little bit more complex function or formula for the logistic regression, just so the logistic regression always gives us a probability like value, and that's all there is to it. So I mean, if you pay attention here, this is the same as this, and this is the same as that one again, right? So these are all the same, and that's all there is to it. And E, of course, is a constant, around 2.77. It's the natural data. I mean, actually, we can see sort of a closer estimate using our program. So if you say exponential 1 here, it gives you sort of like, the very close value, 2.7. Actually, this has much more, numbers. So this is actually an estimate itself here. But anyway, so that's E, and so there's been research and development that the result of this function is a probability like value, and that's all there is to it. So now instead of fitting our data to this equation, we fit it into this equation, and we see how things will turn out. Okay, let's go ahead and do that in R. So this is that part. So instead of using a linear model, I'm using a general linear model. This is the same formula as far as what I'm giving to R. This one, the same formula as far as what I'm giving to R, but now I have to sort of specify the family of the model I'm using, right? So this is the property family of the property general linear model. And say I want to use binomial, link, logistic, right? And the data is there. So once I run this code runs the logistic regression. I mean, some of these things may sound, sort of a random way of presenting things, but this is the way, R has it. So we just have to type that, right? Anyway, so, the thing is, this line of code will run the logistic regression for us. So that's all we need to know. So once I run this and I look at the, actually I have to run this. Once I run this and I look at LRM, oh sorry, I didn't want to mess with my code. So it's LRM. So once I run this, now I have my coefficients. These are my coefficients, and of course I can also run the summary of it. So let me run the summary of that as well. So let me copy this. Actually, this needs to be here as well. LRM. So let me run this summary and see how our model is sort of doing. So again, we see that the score is significant, also the intercept. So that's great. So we can go ahead and run our prediction. And when we do that, we see that all of our values, which is predict 2, now are between 0 and 1, right? So those cases that were the case of negatives, remember which one were the one that were negative? Let's see. Case 9 was negative, so it has to be like very close to 0 as well. So the case 9 is actually the smallest value here as well. And the case 16, which was very close to actually very larger than 1, is actually 1 here, right? So that's the advantage of logistic regression. We can actually rely on these values as probability-like values. There you have it. All right, so that was logistic regression, and instead of using a linear probability model, we are using this function for this to be estimated, and we do that. And once we find the betas for this equation, now we use these values for income and score in here, and then it would give us a probability value, which would be very meaningful for decision making. All right, so let me offer some summary here. We did some recap of prediction, classification, and regression analysis, and then we talked about what's a linear probability model, and we saw its shortcomings, and we made our way into logistic regression. We saw how it was done and how it can be meaningful for us. Until the next video.